Okay. Um, net change theorem. So I wanted to briefly go over, we already went over the first and second FTC. So this is now the third main topic of 5.4. 5.4 is very important. The net change theorem. I don't love the fact that they call it a theorem. Most of the theorems that we really use formally as theorems are existence theorems like MVT, IVT, mean value theorem, intermediate value theorem. What is it? The squeeze theorem, those kinds of things. Then the first and second fundamental theorem of calculus. So those are theorems, but they're kind of more like formula theorems, but super important. But not like formally necessarily used and always named as theorems. You just kind of use them. This net change theorem, you don't really need to know the name net change theorem. I don't see them ever asking you to like cite the theorem or whatever. And I don't even like the way the book writes the formula for the net change theorem. So I'm going to write down that this is the net change theorem, but I'm going to put it in quotes to just be like, okay, this is what the book's calling it. Sorry. Right, so I would just kind of say like, side note, not really a formal theorem. Right, so like when we talk, especially as we start like reviewing toward the end of the year about like, oh, okay, what's like our main theorems? You wouldn't be wrong to say net change theorem is, I guess, technically a theorem, but I wouldn't really mentally put that in that group. Okay, so we're on page 327, but I'm not going to write down, I'm not going to phrase the formula the way they do. So they say, in words, the net change theorem, the definite integral of the rate of change of a quantity f prime of x gives the total change or net change in that quantity on the interval, right? Net means like total, right? Net, this is like total, right? Like your net increase or something is like your total increase. Okay. Okay. I'm not even necessarily going to write down those words. Meh. It is what it is. And I'm also, they use the capital F in this formula. I feel like that just really confuses things, because then really kind of what they're implying is that the integral of the derivative of the antiderivative is equal to the difference of two values of the antiderivative. That's too much for my head to wrap around, and it's not. No. There's no need to use a capital F there, so we're not going to do it. So I'm saying, okay, come on. All right. I'm using just lowercase f, all right? So the integral from a to b, it's a definite integral. Now this is super important, right? This has to be, right? This is the integral of a derivative, right? Super important. Now notice it's not the integral. Anyways, we talked, the second FTC was the derivative of an integral, but that integral was an accumulation function. So obviously this is a little bit different. Because our lower bounds and upper bounds here are just known numbers a and b. All right, so that equals f b lowercase f, just normal, minus FA. Just in case that F kind of looks a little bit funny, let me rewrite that. Okay, so this is just saying, like, if you take, I mean, really, if you think about it, right? If you flip back in your book, again, hopefully you have your books. It's so much easier for me to reference the books when I'm here and when I'm not there in person. If you flip back in your book to 318, the bottom, the first FTC, right? This is like exactly what the first FTC says, except the first FTC says the definite integral of a normal function f from a to b is equal to the antiderivative at b minus the antiderivative at a. Okay, so that goes from the original f to antiderivative f minus antiderivative f. Here, we're just kind of like going like a step forward in derivatives. So instead of going from the original backwards to the difference in antiderivatives, here we're starting as the integral of a derivative and going backwards to the difference of function values, like f values. Okay, so really it's just like a common sense application of the first FTC, right? So this is just like just an application of the first FTC, right? That's all it is. It's really no new information. All right. It is very useful though, in a couple different ways. First of all, and I'm not going to write this down because this should be a fairly common sense thing of its like obvious application. If you look on page 327, example 9, using the net change theorem. A chemical flows into a storage tank at a rate of 180 plus 3t liters per minute. Again, when you're reading these word problems, it's a rate. Warning, warning, right in your head, that's like, f prime or whatever prime. Derivative, first derivative, liters per minute. Also, just looking at the units, you can tell it's a rate, first derivative. Warning, warning, at time t in minutes, blah, blah, blah. Over the interval 0 to 60 for t. Find the amount of the chemical that flows into the tank during the first 20 minutes. Okay, so let's go ahead and let me go back and let's make sure we understand what this net change theorem is saying and then how it's going to apply to this rate of change. Okay, so this is essentially saying, right on the right side, we have the difference between two function values, right? And this, right, if this is related to something that's changing, and like in this situation, we have, some chemical flowing into a storage tank. So what we're saying in F in our kind of chemical example represents the amount of chemical in liters in that storage tank at time t minutes, right? So in this case, our F of B minus F of A would be the amount in the storage tank and so they're asking about during the first 20 minutes. So what it's really going to be saying is, okay, whatever. I'm going to notate a little bit of this example because it might be useful to see it in context. Example 9. This is on page 327. Right, so they gave you essentially, they're calling it C prime, right? The rate of change of the amount of chemical. So, and they want you to know how much of that chemical flowed into the tank between time 0 and time 20. C prime T T. So essentially, they want to know what's the difference between how much chemical there was at time 20 and how much chemical there was at time 0. Right? So this is, right, so that's where we have the net change idea. The total change in the amount of chemical in the whatever tank between 0 and 20. So this would be how much, like the net either loss or the net gain in the amount of chemical between time t equals 0 and 20, right? So this would be like the net loss or gain of C, which is the amount of liters of the chemical in the tank between time equals 0 and 20 minutes. All right, and again, I'm trying to develop good habits in being very specific, using units for C, using minutes for time. C is in liters. So this is like the net change, right? How much, did I gain 50 liters of chemical or did I lose 23 liters of chemical? I don't know. That's what they're asking for. And in order to do that, according to this net change theorem, aka kind of just following the logic of the first FTC, we can integrate the rate of change of C over that time period, right? Again, over that time period between 0 and 20, right? Right, because if I were to have given you this integral on the left and just said, hey, evaluate it. Well, according to the first FTC, I would take the antiderivative C prime. Antiderivative C prime is just C. Evaluate it at 20, okay, and then subtract whatever that antiderivative C is, evaluate it at 0. Okay, that's what you would do to evaluate that left integral, so therefore that means those two things are equivalent. Right, so we know C prime, we just don't know C, right? So this tells us information about how C has changed between time 0 and 20, even if we don't know C, which is this is also the area, right? This is also the area. Another way of thinking about this is the area under the C prime of T, right? C prime of T curve from X, nope, not X, we're doing T. Oops, T equals 0 to T equals 20. Okay, all right, notice, oh my. Sorry. Okay, sorry, my book was on a volume thing. I think I caught that in time, so hopefully all is not lost. Hopefully you can still hear me. Notice, this is the net loss or gain. Very, very important here, right? Net loss or gain. This does not give us, so for example here, even though we started at T equals 0, right? This is not this value here, right? This is not necessarily equal to 0. So therefore, this integral on the left side does not give you the value of C of 20. It gives you the value of C of 20 minus C of 0. That's important because like in this question, they don't say this because it's not relevant. But later on in time, they might tell you, well, initially there were, I don't know, 500 liters of chemical in this tank, and I want you to find how much of the chemical was in the tank at C equals 20, right? And I'm not going to get too much into this. I'm not going to get too much into this, but side note, on a side note. later on, they're not going to just ask like, what's the change in the amount of chemical between time 0 and 20 or whatever 2 times. They're going to ask, well, how much chemical was in the tank at at time 20, right? Side note, to find C of 20, right? The amount of chemical in the tank at T equals 20, right? So to find C equals 20, right? Notice if you wanted to solve, if I just wanted to solve for this thing here, then I could actually add C of 0 to both sides, add a C of 0 to that side, and I could come out saying C of 20 equals C of 0 plus the integral between 0 and 20 of C prime of T dt. Okay. I do think you're going to have to do that like right now in this section, but very, very, very quickly, this is going to be very important. Very important. In fact, this is going to be the main way you will probably use this quote-unquote net change theorem, is because sometimes, a lot of time, they don't want you to just know, oh, well, how much like extra chemical was added between these 2 times. No, usually they want to know, I want to know how much chemicals in my tank at time after, at 20 minutes. Well, the amount of chemical in your tank after 20 minutes is not just how much was added between time 0 and time 20, though that is relevant, right? It's not necessarily just that, right? But it's also how much you started with. And again, this doesn't have to be 20. This doesn't have to be time 0, right? So again, this is not necessarily, I'm going to point back to here, right? C of 0 is not necessarily 0, right? And I know I'm getting a little bit off topic, but if you can follow me, should I stay in? I'm going to go in black, whatever. It's important enough. I'm going to have to reiterate this over and over again, but essentially going back to the net change theorem, we had A to B f prime of x dx equals f b minus f a, right? We had that. This later on is going to rearrange, maybe even more importantly, to say, all right, if I want to find f at some x value or time value or whatever the input is at b, that's equal to f of a plus the amount of increase or decrease in that function between time or whatever, a and b, right? So this is saying, and sometimes, again, and I know I'm getting a little ahead of myself, but I want to go ahead and write this out, so I'm laying the groundwork. So normally B is later than A, but even if B is actually like if you know how much, say I know how much there is in my tank after 50 minutes, and I want to know how much was in there at 10 minutes, and if I know F prime, and I know how much was in there at 50 minutes, then I could plug in 50 for A and 10 for B and still do this, right? This is also kind of a form of kind of like a differential equation thingy when you know C. Anyways, I'm going to kind of just leave that there. You're probably still scratching your heads a little bit with that. Let me see. I did want to also mention, so the application to like physics and kinematic stuff is very important here. So even the book mentions this. So it says at the bottom of the page of 327, another way to illustrate the net change theorem is to examine the velocity. I'm reading at the bottom of 327. To examine the velocity of a particle moving along a straight line. Where s of t is the position at time t, then the particle's velocity is s prime of t, and yeah, so again, let's see, I'm gonna just come down here. I'm probably gonna go ahead and write that down because that's pretty important. So application to you know what I mean, to position s of t and velocity v of t, which equals s prime of t, right, would be that a b. Now we're going to do this in terms of t instead of x. So the integral, right, of s prime of t dt is equal to s, oops, s of b minus s of a. So therefore, right, so therefore this is equal to the integral from time a to time b of the velocity of t, right, because these are the same. Dt is equal to s of b minus s of a. All right, so what does that mean? That's very important. That means the area, whoa, didn't mean to do that. The area under the velocity curve between time a and b, right? All right, so the area under the v of t, no, curve between t equals a and b is equal to, now this is important, and again, if I was there in person, I would ask you this and see what you thought, s of b minus s of a, what that is indicative of. That is not the distance traveled between time a and time b. Remember, very important, just like velocity is different than speed, displacement is different than distance. Distance is absolute value of displacement. So here, there's no absolute value sign. So this has nothing to do with, this is, well, that has nothing to do with distance. It's not distance directly, it's displacement, which may or may not be the same as distance, right? Equals the displacement between time A and B, right? So the displacement not necessarily the distance traveled. Between t equals a and b. Okay, displacement between a and b. Like for example, if I run 10 miles forward and then run 5 miles backwards, right? My distance traveled sure is 15 miles because I ran 15 miles, you know, I would get that amount of exercise, but my displacement would only be 5 miles, right? Because I like backtracked for 5 of those miles. Okay, and so you can see the top of page 328, definitely look at that as I'm talking. That's super important. I don't want to have to write down everything. Right, so the distance traveled, right, so distance is the absolute value of distance traveled equals the integral from a to b at the absolute value of the velocity. Right, so distance as absolute value is the integral of the absolute value of velocity, right? Which means all area under the velocity curve is counted as positive area, right? So this means all area under, well, you know, like essentially the all, right? Like in this case, you know what I mean. That kind of thing, right? Well, if this is absolute value, right, we would flip this up and count that as positive area as well, right? So we would count all that as positive, whereas for displacement, all area counted. That's not how you spell counted. Counted as all area counted as positive, right? Whereas over here, this area, right, just like if you look at the thing on the page, right? So this is going to be positive area, like positive A1, say, and then this is going to be this is going to be negative area, right? And this would be like plus area 3, right? So that if you run backwards, you subtract that area, you subtract that amount of distance, whatever, traveled from the other distances. Whereas if you're talking about distance itself, anything you run, right, like that's what you would want if you're like running around a track and you're exercising, because if your starting ending position's the same, then technically your displacement's 0, but your distance is like, you know, however many miles you ran. Very important. So, and again, this goes back to, and I already did an absolute value problem, so I'm not going to get into the weeds with this one, but please look through and take notes on example 10. It's very important, especially I think the last time we did something similar to this for like, I don't know, something with absolute value back in the fall semester. People were a little shady on this one. On one like this that had absolute value. So like example 10, particles moving along a line so that its velocity is blah, blah, blah. What's the displacement of the particle between time 1 and 5? That's, you just integrate the velocity from 1 to 5. You don't have to worry about it. Right, it'll take care of itself. A normal integral automatically counts, right? A normal integral is going to count stuff just like this, where if it's if the velocity is below is, you know, a negative velocity, it counts the area between there and the x-axis as negative, right? That's just how integrals work with area. So it would naturally count any time where your velocity is negative, so you're like running backwards, count that as like negative displacement. So you just do it straightforward. B, right, now it's asking for total distance traveled. Now you have, it looks very similar, but just boom, they got to slap this, right? They're slapping this absolute value stuff on there. And when you do that, again, just like I already went over a problem like this, that was a linear problem that was, yeah, one where I don't know, this might have been in the previous, I don't know. Anyways, oh yeah, no, this was the first FTC thing. The big thing is you have to figure out where on the interval the function hits 0, and then determine the intervals on which the function that you're integrating is then positive or negative. So in this case, the interval you're concerned about is 1 to 5. So if it hits 0 outside of 1 to 5, I don't care. if you try to find the zeros of this function, I wouldn't give you one where you would have to factor a cubic like this that doesn't, I mean, technically, use those algebra 2 skills I taught you 2 years ago and you should be able to do it. But I don't think that even the AP would give you one that kind of annoying. Anyways, they tell you right here, it can be factored as t minus 1 times t minus 4 times t minus 5. So looky there, there's zeros of this velocity function at 1, 4, and 5. 1 and 5, doesn't really matter. They're the endpoints. It's kind of a non-issue as to whether they're 0 or not. What we care is whether the function we're integrating changes signs on that interval, and it does. It must change signs at 4, or, well, it probably changes signs because the function hits 0. I guess it doesn't have to, but we need to investigate whether it changes signs. And yeah, sure, it's easy to do this when you see the function, just like, oh, well, yeah, look, there's the graph. The problems I'm going to give you, I'm not going to just give you a graph. So you're not going to just be able to look at it and be like, oh, duh, great. So I just integrate the function from 1 to 4, and then the function becomes negative 4 to 5. Great, so I subtract that, bada bing, bada boom. You're not going to know that. So you're going to actually have to set the function you're integrating, set it equal to 0, and then plug in, kind of pretend like it's a first FTC type problem. Not first FTC. Oh, everything's getting mixed up in my brain too. First derivative test problem. Remember that? Where you found like critical numbers, plugged in x values on like either side of that and did like the little like interval chart thingy. Anyway, so similar to that, you need to figure out, okay, great, function hits 0 at 4, so I need to plug in a number between 1 and 4 to the velocity thing, see if it's positive. It's positive. Plug in a number between 4 and 5. That's going to be kind of annoying, but you should get a negative number, right? So where the function is positive, you just get to integrate it like normal. So you'll notice down below that, you just integrate from 1 to 4 like normal. But then you have to break it up and do a separate integral from 4 to 5. And since naturally that function is going to yield negative values, right? Negative velocity values. Since we want to count all velocity as positive velocity, right? All running as positive running. Like, hey, I want to count all of my calories toward my weight loss goal or something, whatever. Since the velocity is negative there, you actually need to negate the negative. So you actually subtract the integral from 4 to 5, right? So that it turns out that it's actually positive, which you should see below in the second to last step. When you have those two integrals, of 45 fourths minus a negative 7 twelfths. So that's how that should look, right? Because you can see that you're actually subtracting a negative so that you're actually counting that as positive. And that's 71 sixths. But I will also note that if I were doing this problem by hand, it's going to be a lot more annoying by hand than it looks. Because you'll notice with that whole polynomial, you got fourths, thirds, halves, and then some whole number stuff. Instead of keeping it all separate and having one value for that whole first integral and then one value for that whole second integral, what I would do is I would combine the fourths together, right? So, because you're going to have, right, whatever 4 to the 4th fourths are, minus 1 to 4th fourths from the first one. And then also from the second integral, you're going to have 5 to the 4th fourths minus 4 to the 4th fourths. And again, very important that you put everything after the subtraction sign in like giant, giant, giant brackets. Yeah, problems like this can get kind of icky. I'm not going to give you ones that are like too icky. I don't know. I can't promise anything. Well, I can promise that they're not like absolutely horrible. This would be like the worst they would ever get, but this one's pretty annoying. They just don't write out all the steps. But anyways, I would combine like all the fourths together, all the thirds together, all the halves together, all the whole numbers together, and then kind of from there. Because if you don't do that, then you're going to be combining fourths and thirds and halves and whole numbers on 4 separate occasions when you plug in 4 and 1 and 5 and 4. Yeah. Also notice you're plugging in 4 on 2 different occasions and then you're subtracting them. So if you play your cards right, that would help you too. Anyways, be smart, use efficiency, pattern recognition. Okay, I think that's all I had to say for this section. Like number 67 on the homework, it's asking you to estimate the distance a car travels in 8 seconds. In 8 seconds. Okay, so only for... Oh, I see. So that means you're only looking at, I guess, from 0 to 8, I assume. And using the net change theorem, essentially, you know it's just the area under the velocity curve between 0 and 8. So you're literally just approximate. It says approximate or estimate. So you're literally just like counting boxes and approximating by examining the area of boxes under that curve. That's not bad. All right, I think that's all I have to say. So I guess again, goodbye, good luck, well wishes to you all.